the last lecture we considered some examples of context free grammars, the grammars and the language generated by them. Today we shall consider some more examples. The first example we consider is this. There are two non-terminals S and B and three terminal symbols A, B and C, and there are four rules. The rules are of the form S goes to A, S, B, C, S goes to A, B, C, then C, B goes to B, C, B, B goes to B, 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 this is small b. Now, you can see that this is not a type 2 grammar or a type 3 grammar, because on the left hand side if you have a single non-terminal it is type 2. But here you find that on the left hand side you have a string CB and BB here. So, this does not belong to type 2, but you can also see that the length of the right hand side is always greater than or equal to the length of the left hand side. So, this is a type 1 grammar. And let us see what are the strings, terminal strings generated in this grammar. The language generated by the grammar consists of all terminal strings derivable from the start symbol S. So, we will see what are the terminal strings derivable. So, using rule 2 alone, from S you can derive A, B, C using rule 2 alone. So, A, B, C belongs to the language. A, B, C belongs to L of G. Now, starting from S, if you use rule 1, you will get A, S, B, C. Now, again for this S you can use rule 2, then you will get A, this S will be replaced by A, B, C, this A, B, C, then this B, C remains as it is. This is not a terminal string. Now, you can apply the rule 3 CB goes to BC to this CB. So, this CB becomes BC. The idea of this rule is to bring all the C's to the right and the capital B's to the left. Now, this is applying rule 3, then applying rule 4, this BB can be, this capital B, when there is a small b on the left side will be turned into a terminal B. So, rule 4 you apply and you get AB, AA, BB, CC. This you can represent as A squared, B squared, C squared, and this belongs to L of G. Now, let us consider one more example. I will start from here. S, use rule 1, you get A, S, B, C. Then again use rule 1 for this S, then you will get A, S, B, C, this S is replaced by this A, S, B, C, but this B, C will remain as it is. Now, apply rule 2 for the S, then you will get A, B, C, this B, C will remain as it is, this will B, C will also remain as it is. Now, use rule 3 repeatedly to bring the capital B's to the left and shift the small c's to the right. So, you will have A cubed B, if you apply the rule for this CB you will get B, this B is here, then you will get BC, C, B, C. Again you apply rule 3, A cubed B, B, C. If you apply to this CB, B will be shifted to the left and C will be shifted to the right. you will get A cubed BB CC. Now, again to this CB you can apply rule 3. So, you will get A cubed B B B C C C. Now, you see that all the terminal C's are shifted towards the right, all the A's are on the left. Now, you have one B and capital B's in the middle. The capital B's have to be converted into small b's using rule 4. So, apply rule 4 repeatedly, you get A cubed B B B C cubed. Again you apply rule 4, A cubed B B B C cubed. So, the string generated is A cubed B cubed C cubed belongs to LG. Now, you can see the pattern. What will be the language generated by the grammar? The language generated will be L of G will be A power n, B power n, C power n, n greater than or equal to 1. So, this is a type 1 language or a context sensitive language. This cannot be generated by a type 2 grammar. In type 2, what happens is when you replace by another non-terminal, you can generate equal number of A's and B's. We considered an example where you can generate A power n, B power n. But you have to keep the same count for A, B and C. For this, something else is required. You have to shift the, as in this example, you have to shift the C's, generate equal number of B's, C's, etc., but then shift the B's to this side and shift the C's and so on, and that requires some context. So, this cannot be generated. Later on we give a formal proof that it cannot be generated by a type 2 grammar after learning some theorem, but at present we will just make a note that this is a type 1 language which cannot be generated by any type 2 grammar. Now, to generate A power n, B power n, how do you go about? To generate A power n, B power n, C power n, how do you go about doing this? First, you from S, rule 1 you have to apply repeatedly. I will put star. You have to use rule 1 repeatedly. When you use rule 1, S will be replaced by A, S, B, C. So, one A will be generated on this side, one B, C will be generated on this side. So, n minus 1 times if you apply rule 1, n minus 1 times, you will get A power n minus 1 S B C n minus 1. Okay, BC, BC, BC like that. Then you apply rule 2 once, you will get A power n BC BC power n minus 1. So, this you can also write as A power n B C B to the power of n minus 1 C, right. Now, all this C B, you have to shift the capital B to the left and small c to the right, for which you have to use rule number 3 there, C B goes to B C. How many times you have to apply this? There are n minus 1 CBs. So, how many times you have to apply this? If you can apply the rule n minus 1 times to this, but then at the end one capital B will come here, but then you will again have n minus 2 CBs. So, after applying say rule 3 n minus 1 times, what you will get is a power n b b C b power n minus 2 C. Right. Now, again to this n minus 2 CBs you have to apply the rule again. That will end up with n minus 3 CB in the middle, you have to apply again and so on. So, ultimately when you get a power n b this is again star b power n minus 1 c power n, when you get this, how many times you would have applied rule 3? You would have applied it n minus 1 plus n minus 2 plus 1 times. What is this value? N minus 1 into n by. So, you would have applied rule 3 so many times. For example, when n is equal to 1, you do not apply that rule at all. When n is equal to 2, you are applying n minus 1 into n by 2 is 1, you are applying rule 3 only once. When n is equal to 3, what is n minus 1 into n by 2? 2 into 3 by 2, that is 3. 3 times you are applying, check, you are applying 3 times. So, when you want to generate a power n, b power n, c power n, first you have to apply rule 1 n minus 1 times to get a string of this form. Then this is equivalent to this, and you have to you get this, and then you apply rule 2 once to get the ABC. Get rid of that S, you have to use rule 2. Then when you get a string of this form, you have to bring all the capital B's to the left and small c's to the right. So, you have to apply the rule CB goes to BC repeatedly. So, first time you can use n minus 1 times, then again n minus 2 times and so on. So, you will be using that rule n minus 1 into n by 2 times. When you do that, you get a string of this form. Then finally, rule 4 is used to convert all the capital B's, which is a non-terminal. Capital B is a non-terminal. Those B's have to be converted into small b's. So, how many times you will be using rule 4? Rule 4 will be used n minus 1 times. So, ultimately you get. So, you must realize that if you have a C, you cannot C to the left of B, you cannot convert the capital B into a small b. Only when the B gets shifted in the middle towards the B, the capital B gets converted into a small b. So, you make sure that all the B's are shifted. If you write B goes to B in the middle, some of the B's you can replace in the middle also, that you do not want. So, you want to convert the capital B's into small b's only when they are shifted to the middle. That is why this rule is there. This rule makes sure that all the capital B's are shifted to the left, then you are converting them into small b's. Okay. So, this is a very simple example of a context sensitive language or a type 1 language. Now, we have seen the grammar for a power n, b power n. We gave a grammar in the last lecture for this. Context, this is type 2 we gave, and a power n, b power n, c power n Today we have considered a type 1 grammar. I will consider one more, a power n, n greater than or equal to 1. What grammar can you give for this? Consider this grammar with S as the non-terminal, only non-terminal, and the only terminal is A, and the rules are of the form S goes to AS, S goes to A. There are only two rules, S goes to AS, S goes to A. So, with this you can see that applying the second rule alone you generate A, applying rule 1 and then applying rule 2 you get AA, and so on, AA belongs to LG. Similarly, applying rule 1 n minus 1 times, applying rule 1 n minus 1 times and rule 2 once, you will get A power n. So, the language is this, the language is this. What type of a grammar is this? This is a regular grammar or a type 3 grammar. Actually, you will find that there are slight difference definitions given for type 3. So, the way we defined is type 3 we defined is the rules are of the form A goes to AB, something like this, left hand side a non-terminal, right hand side as terminal symbol followed by a non-terminal, or like this, a non-terminal going into a terminal, or you can also have something like A equals to epsilon. Okay. Sometimes, for example, for example, in this one, instead of this, if I have epsilon, what will be the language generated? The empty string also will be generated, right. So, you will get the language as A power n, n greater than or equal to 0. Okay. Sometimes the definition of type 3 is given like this. On the left hand side you have a non-terminal, on the right hand side a terminal string followed by a non-terminal, or a non-terminal going into a terminal string. So, right hand side you can have a terminal string, it is a string, W is a string, W belongs to T star, W belongs to T star, and B goes to W, that is on the right hand side you can have a terminal string followed by a non-terminal or just a terminal string. It can be empty string also. Now, the point to be noted is this capital B, which is a non-terminal, occurs only, there is only one non-terminal on the right hand side, and that is the last symbol. Okay. This definition is also considered as right linear grammar, right linear grammar. Even though you write like this, these two definitions are equivalent. What is the reason? Suppose I have a rule of this form. I have a rule of the form, say A1, A2, AN, B. This is a string instead of a single symbol. all are terminal symbols, A1, A2, An are all terminal symbols. If I have a rule like this, I can split this into several rules of this type. How is that possible? I can introduce new non-terminals, A going into say A1, A1 goes to A2, A2 goes to A3, like that up to An minus 2 goes to An minus 1, An minus 1. Then An minus 1 goes to Anb. Now, each one of this rule is of that form. Left hand side you have a single non-terminal, on the right hand side you have a single terminal followed by a single non-terminal. You are introducing new non-terminals A1, A2, A3, An minus 1. So, the application of a single rule of this form is equivalent to applying a sequence of rules like this. If you apply this first, then this, then this, then this and so on, the effect will be the same as applying this rule. So, this rule in essence you can split in this form. So, even though you consider this definition or this definition, they are equivalent, whichever way you consider, it is immaterial. Now, as for the present, we will keep the definition like this. It does not make much of a difference if you consider like this also. Or equivalent you can also have in this form. This is also will generate the same type of language, B W, B goes to W. The only non-terminal on the right hand side, it can occur at the last symbol or it can occur as the first symbol. Such a grammar is known as a left linear grammar, Again, this also generates the same type 3 language, but you must not mix up this and this. In the same grammar, either you should have all the rules left linear or all the rules right linear. If you have one left linear and one right linear, that no longer it can generate a higher class. So, these grammars generates what are known as regular sets. The language generated is called a regular set. The regular set is also, any regular set is accepted by a finite state automaton. The equivalent machine characterization is FSC. So, let us consider one more example. The non-terminals, there are 3 non-terminals now. Another grammar we will consider. This is of type 2. The terminal symbols are A and B. There are 8 productions. The production consists of S is the start symbol, and the production symbols, production rules are like this. S goes to AB, B goes to B, B goes to BS, B goes to A, S goes to BA, A goes to A goes to AS, A goes to BA. S is the start symbol, right. There are 8 rules, 2 terminal symbols A and B and 3 non-terminals S, capital A, capital B. Try to generate a few strings in the language. What are the strings generated? Let us try to generate some strings. S goes to AB, rule 1, then rule 2, you will get AB. S goes to BA, rule 5, rule 6. You can generate AB, you can generate BA. Then you can also generate S goes to AB, rule 1, rule 3 if you use AB, S, then rule 5, AB, BA, rule 6, AB, B, you can verify that length 2 AB can be generated, BA can be generated, length 4 AB can be generated, AB, BA can be generated, BA can be generated, BAA can be generated, AABB can be generated, AABB, BBAA, ABBA, BAAB, BAAB also can be generated, BABA, ABAB. In general, you will find that you cannot derive strings of odd length, you will be able to derive only strings of even length from S, and also that will have equal number of any string generated in this grammar will have equal number of A's and B's. It is not very obvious. See, looking at the rules, that is not very obvious, is not it? So, we will have to prove that, right? We have to prove. So, in general, what your purpose will be, given a new language, you want to design a new language, programming language and construct the compiler, means first step will be to generate the grammar. You are for framing the grammar, but then you must show that this grammar generates all syntactically correct programs in the programming language you are designing, and all syntactically correct programs can be generated by the grammar. That is, the grammar generates all syntactically correct programs in the language and only those, not anything else. So, that way you have to prove, then only you can proceed for constructing the compiler. So, this is, for example, here we know that the language generated has any string which has got equal number of A's and B's. That is not very obvious from the grammar, is not it? So, you have to prove that. How do you prove? We will prove by induction. So, the inductive hypothesis is this. If a string is derivable from S in this grammar, then or if and only if W has equal number of A's and B's. But this is the one we want to prove, but in order to prove that we need to prove something more also. String is derivable from the non-terminal A if and only if W has one more A than it has B's. Then another step would be a string is derivable from B, a terminal string, W is a terminal string, if and only if W has one more B than it has A's. So, this is the inductive hypothesis. So, taking the basis class, induction is on the length of the string. Induction, you must note that there are two things. If every statement has if and only if, so you have to prove in both directions, right. So, induction, for induction basis, you can note that no string of length 0 epsilon empty string cannot be derived from any non-terminal here A, B or S. When the length is 1, from A you can derive A, it has 1 A and 0 B's. So, the induction hypothesis is satisfied. From B you can derive a B which has got one more B than it has A's. So, the induction hypothesis is satisfied. From S we have seen that you can derive AB or BA, that is the smallest string you can derive from S, and that has 1 A and 1 B. So, it has got equal number of A's and B's. So, the basis class for n is equal to 1, n is equal to 2, you have checked, right. So, the basis class holds. Then the induction class, we have to prove the induction portion. We will just prove this first statement alone. The second and the third can be proved in a similar manner, just a matter of details only. So, let us take the first one only. We will assume that the inductive hypothesis is true up to n minus 1. Okay. So, assume up to n minus 1. Up to n minus 1. This n is the length of the string, length of the string. Induction is on the length of the string. Assume up to n minus 1, that assumption is all the three you are assuming up to n minus 1. Okay. Prove for n, prove for n. Okay. So, if you have a string W belongs to T star and the length of W is n, you have to prove that S derives W if and only if W has equal number of A's and B's. So, there are two parts. If S derives W, then W has equal number of A's and B's, and the other way around, W has equal number of A's and B's, then it is possible to derive W from S. You have to prove two ways on two directions. If it is possible to derive W from S, then W has equal number of A's and B's. And if you have a string W which is having equal number of A's and B's, it should be possible to derive that from W. Both ways you have to prove. Let us see how to go about this. First, assume from S W is derivable. Okay. So, what you do is from S, if you start from S, you have to use rule number 1 or 5, right. If you use rule number 1, the first step will be like this. If you use rule number 5, the first step will be like this. Okay. Then from B, you are deriving a string W1 in many steps. And you are getting a string AW1 which is equal to W. Okay. So, W1 is derived from B, and what can you say about the length of W1? Length of W is n. So, what can A is taken away? So, what can you say about the length of W1? N minus 1, right. And the induction hypothesis holds for all strings up to n minus 1, that is strong induction. All strings up to n minus 1 it holds. So, if W1 is length of W1 is n minus 1 and it is derivable from B, what can you say about this? A string W is derivable from B if and only if it has one more B than it has S. So, W1 has one more B than S, right. So, along with this A, what can you say about W? W will have equal number of A's and B's. Therefore, W has equal number of A's and B's. This one if you take S goes to B, if you have the first rule is like this, then from A you are deriving a string W2. What can you say about the length of W2? This is equal to W. Length of W is n. So, length of W2 is n minus 1 and W2 is derived from A. So, by the induction hypothesis, what can you say? A string is derivable from A if and only if it has one more A than it has B's. So, W2 has one more A than B's. So, counting along with this B, W has equal number of A's and B's. So, this is one portion. What we have proved is this: if a string is derivable from S, then it has equal number of A's and B's. The other way around we have to prove. If you have a string which has got equal number of A's and B's, it should be possible to derive that from S. That way also you have to prove. So, how do you go about proving that? Assume that length of W is n and W has equal number of A's and B's. Now, you have to show it is possible to derive W from S. You have to show that it is possible to derive W from S. Now, there are two possibilities. W is a string of A's and B's. There are two possibilities. The first symbol can be a or the first symbol can be a B. So, it is possible that it is AW1 or you can write W as BW2. Okay. And what can you say about W1? Length of W1 will be n minus 1 and W1 has, W has equal number of A's and B's, one A is taken out. So, W1 has one more B than A's. So, by the induction hypothesis, it should be possible to derive W1 from B. So, by inductive hypothesis, it should be possible to derive W1 from B. But we have a rule, S goes to AB. We have first rule is this. So, apply this rule, then from B you derive W1, that is from S you can derive W. Okay. So, if W has equal number of A's and B's and assuming that it begins with the A, it is possible to derive W from S. That is what we have proved now. Now, second case, take W is equal to B W2. So, what can you say about the length of W2? The length of W2 is n minus 1 and W2 will have one more A than it has B's. W2 has one more A than B's. So, by the induction hypothesis, what do you get? It is possible to derive W from A if it has got one more A than it has B's. So, by induction hypothesis, it should be possible to derive W2 from A. So, but we know that there is a rule of the form S goes to BA, rule number 5, S goes to BA is there. Apply this first, then from this A you can derive W2, but BW2 is nothing but W. So, it is possible to derive W from S. So, the language generated consists of equal number of A's. Any string having equal number of A's and B's will be generated by this grammar. What is the difference between this and the Dyck set which we considered in the last class? Dyck set is the well formed strings of parenthesis. So, for example, if you look at A as the left parenthesis, B as the right parenthesis, this will belong to the language, this will belong to the language, but this will not, because this will be right left left right like that, which is not a well formed string. So, there is a difference. Here any string will have equal number of A's and B's. Dyck set also any string will have equal number of A's and B's, but there is some more restriction. What is that restriction? Left should come first. I mean, the well formed string parenthesis means left parenthesis should come before the matching right parenthesis. Okay. Now, one more point to note is, can this grammar generate the empty string? This grammar cannot generate the empty string. The smallest string generated by the grammar is of length 2, A B or B A. A alone can derive A, B can derive B, but from S the smallest string derivable is of length 2, A B or B. Now, I will write another grammar. Look at the rules. There is only one non-terminal, S. Terminals are A and B. The rules, there are 3 rules. S goes to SA, SB, S. S goes to SB, SA, S. S goes to epsilon. A set of projections consists of these 3. Here the empty string can be generated, okay. The empty string can be generated here, but you can see that whenever I apply rule 1, 1A and 1B will be generated. Whenever I apply rule 2, 1B and 1A will be generated, but ultimately any string generated will have equal number of A's and B's. In between some of the S's you can make it go to epsilon. So, it is very obvious that any string generated by the grammar will have equal number of A's and B's, but you have to prove the converse also. Any string having equal number of A's and B's will be generated by this grammar. That is not as easy, that is not very trivial. One direction it is very easy to see. Any string derivable in this grammar will have equal number of A's and B's. But if the language consists of all strings having equal number of A's and B's, you must also prove that any string having equal number of A's and B's will be generated by this grammar. You can try this. That is not very trivial step. You have to prove that. Now, the Dyke set, the grammar which we gave was this: S goes to SS, S goes to ASB, S goes to AB. Here again note that epsilon cannot be generated, the empty string cannot be generated. An equivalent grammar which will also generate the empty string is this. That is, in this grammar leave out this, have these 2 rules alone. This again will generate only well formed strings of parenthesis, but in this case epsilon is generated, in this case epsilon is not generated. Similarly, these 2 generate the same language apart from epsilon. Here epsilon will be generated, epsilon will not be generated in the other one. So, these are some of the examples which we consider for type 2 and type 3 and type 1 also we have considered one more examples. In the next lecture we will see some more example and also about ambiguity. By the way, you can try to prove that the other converse of it, that is any string having equal number of A's and B's will be generated by this grammar.